Alright guys, in this section we're going to be discussing concavity and the second derivative test. In the previous section we were already seeing how locating the intervals on which a function f increases or decreases helps us describe the graph of the function. In this section we'll see how locating the intervals on which f prime, in other words the first derivative, increases or decreases, can be used to determine whether the graph of the function is curving upwards or curving downwards. So this is what we're going to refer to as concavity. First of all, we're going to look at the definition of concavity, and we have that if we have a function differentiable on an open interval I, the graph of f is concave upward on I if the derivative of f is increasing on the interval, and it's concave downward on I when the first derivative is decreasing on the interval. So here we have a visual representation of concavity. So let's say we have our function f and we start looking at the derivative of f. We know the derivative of the function represents the slope of the tangent lines. So all these slopes here of these red lines on this graph are increasing. Because notice how coming from the left to the right, I'm going as negative slope. At some point it turns and it starts increasing. The slope of that tangent line starts increasing. Same thing for the other way around. Right? We have slopes starts with a positive slope, and then it turns. At some point it turns on the maximum there, and it comes back down. And the slopes are negative. So this is what makes a function concave upwards or concave downwards when the first derivative is increasing. So that's what the definition is saying. The first derivative increases, is concave upwards or concave up. If it decreases, it's concave down. Okay, so we're going to have a test for concavity here, and since we're really looking at whether the first derivative increases or decreases, that's like seeing the sign, whether it's positive or negative, the sign of the derivative of the first derivative, which is, in other words, the second derivative. So that's what this theorem is saying. If the second derivative is greater than 0 or positive for all x's in that interval, then the graph is concave up on that interval. If the second derivative is negative for all x's in I, then it's concave down. So here we have an example where we're asked to determine the open intervals on which the graph of the function is concave up or concave down. And we have a nice polynomial here of degree 4. F of x is equal to x to the 4th minus 3x cubed. Okay, the first thing we're going to do to find concavity is to find the first derivative, of course. And f prime of x is going to be equal to 4x cubed minus 9x squared. Next, we're going to find the second derivative. Because remember, the test for concavity uses the second derivative. So we're going to go ahead and find that. And that's a pretty straightforward calculation here since we have a nice polynomial. F double prime of x is going to be equal to 12x squared minus 18x. And we're going to set this equal to 0 so that we can test the intervals, and in this case in the whole number line, since this polynomial is defined everywhere at all the real numbers. We factor it, set it equal to 0, set each factor equal to 0, and we get that 6x is equal to 0 and 2x minus 3 is equal to 0. From there we get our x equal to 0 and x equal to 3/2. So these numbers are going to split the number line. It's sort of similar to what we did on testing whether a function was increasing or decreasing with the first derivative on the previous section, but now we're doing it on the second derivative, and the second derivative is going to determine concavity here. So we have our number line, and we're going to apply similar process. We're going to do a similar process that we did on the previous section, but now remember, keep in mind that we're testing these test values on the second derivative, right? So we pick a number on each interval, within each interval, and we're going to evaluate those numbers at the second derivative here. So the first one, I picked -1 on the interval negative infinity to 0, and I evaluate it on the second derivative, and I get, of course, you just plug it in, 12 times -1 squared minus 18 times -1, and we get that's equal to 30. All right, we do the same thing for our other two test values. Evaluating the second derivative at 1, we get is equal to -6. And finally, second derivative at 2 is equal to 12. Now remember, all we care about are the signs here. So as you see on the first one, on that first interval, we got a positive. It was 30, so that's the whole interval is going to be positive for that second derivative. Remember, we're testing the second derivative here. And that second interval from 0 to 3/2 is negative, and from 3/2 to infinity is positive. So this is going to be the concavity. And for all the positives, we have concave up, and for the negatives, we have concave down. All right, so writing this formally, we have the intervals where the function is concave down, we have 0 to 3/2, and for the intervals where the function is concave up, we have negative infinity to 0, union 3/2 to positive infinity. And there we have it. All right, here we have another example where we have a function equal to 2x minus tangent of x, and they give us an interval from -π/2 to π/2. Okay, doing the same process here, we're going to find first and second derivative. We really just need the second derivative for concavity, but we need to find the first one to get to the second derivative. So f prime of x is equal to 2 minus secant squared of x. You already know your basic rules of differentiation. And then we take a second derivative, right? Second derivative would be derivative of 2 is just 0, and the derivative of secant squared is negative. We had a negative in front. 2 secant x times, and then chain rule, we'll multiply that by secant x times tangent x. Cleaning this up a little bit, we get -2 secant squared of x times tangent of x equal to 0. And then we have two factors here, which we said each one equal to 0. And we're going to get that from secant squared x equal to 0. We just get secant of x is equal to 0. But that turns out to be undefined or does not exist because secant cannot be 0. It's outside its range, 0. And we get that tangent of x equal to 0, and that happens when x is 0. And remember, we have to stay within that interval that's given -π/2 to π/2, so that's the only one that fits there. That's my only point here to plot on the number line. We're not doing the whole number line since we're giving an interval, so I'm going from -π/2 to π/2 and with 0 there in the middle. And we're going to test, I'm just going to pick nice numbers here, -π/4 and π/4, one on each interval. And then we're going to evaluate those in my second derivative. So when I evaluate -π/4 into my second derivative, I'm going to get -2 secant squared of -π/4 times tangent of -π/4. So that is equal to 4. In the same way, we're going to do evaluate π/4 into my second derivative, very similar procedure, and we're going to get -2 secant squared of π/4 times tangent of π/4, and that's equal to -4. Okay, so we get our signs for each interval. The interval from -π/2 to 0, I have that the second derivative is positive, and the interval from 0 to π/2 is negative. Remember, this is the second derivative, which indicates concavity. So formally, we have that the function on this interval is concave down from 0 to π/2, and is concave up from -π/2 to 0. And there we have it. Another definition that we'll see in this section is the definition of point of inflection. So given a function that is continuous in an open interval, and having a point on the interval, if the graph of f has a tangent line at the point c, comma f of c, then this point is a point of inflection of the graph of f, when the concavity of f changes from upward to downward or downward to upward at that point. In other words, if you change concavity either from concave up to concave down or concave down to concave up, that point where that changes when you change concavity is what we call a point of inflection. And points of inflection, we have this theorem now that says that points of inflection happen either at when the second derivative is equal to 0 or when the second derivative does not exist. Very similar to when we evaluate or try to find critical numbers on the first derivative. This is for points of inflection, a similar procedure for the second derivative. Here we have an example where we're asked to find the points of inflection and discuss the concavity of the graph of the function. And we have a nice function here, a cubic function, and f of x is equal to x cubed minus 9x squared plus 24x minus 18. First of all, we need to find the first derivative. So f prime of x is going to be equal to 3x squared minus 18x plus 24. From there, we're going to go ahead and calculate our second derivative, and that's going to be 6x minus 18. From there, to be able to find intervals of concavity, we need to set that second derivative equal to 0 and find those solutions. From there, we get that x is equal to 3, and there's only 1 there. Now, remember, the point of inflection is going to happen either, if there is a point of inflection, it's going to happen when the second derivative is 0 or undefined. Now, in our case, there's no undefined because this is a polynomial, so only when the second derivative is equal to 0, and we saw that we got a x equal to 3. So that's a possible point of inflection. We're going to check the concavity, so what we did on the previous example. Let's check what happens before and after 3. And if it changes concavity, whether going from up or up to down or down to up, then we'll conclude that 3, at x equal to 3, we have a point of inflection. So evaluating a test number, a test value before 3 and after 3 on the second derivative. That should have been the second derivative there, guys. It's a little typo, but we are evaluating at the second derivative, which is 6x minus 18. We get that the first interval from negative infinity to 3 is negative, in other words, concave down. And the second one from 3 to positive infinity is positive. The sign of the second derivative is positive, so it's concave up. The point is, it does change concavity at 3, at x equal to 3. Therefore, there is a point of inflection at 3, comma, the function evaluated at 3. If you want to find the actual y value, just plug in 3 or evaluate the function, the actual function, f of x, at 3. And doing that, we're going to get 0. We actually get 0 there. So this is actually a 0 of this function. That was just a coincidence, but it's also a point of inflection, 3, 0. Okay, so here we have another example. F of x equal to 2 sine of x plus sine of 2x. And the first thing we're going to do is find the first derivative. We get f prime of x is equal to 2 cosine of x plus 2 cosine of 2x. Now, in this function, we're only going to consider the interval, the closed interval 0 to 2 pi. So the second derivative is equal to negative 2 sine of x minus 2 sine of 2x times 2, because of chain rule, so that 2 with the 2 in front will multiply into a 4. We want to see where the second derivative is equal to 0. We rewrite negative 2 sine of x, and I'm going to use my double angle identity here from my trig class to rewrite 4 sine of 2x into 8 sine of x cosine of x. Remember, sine of 2x is equal to 2 sine x cosine x, so that's a well-known identity from trig. After doing that, I see that I have a negative 2 sine x in common. I factored it out, and I get that times 1 plus 4 cosine of x. All of that equal to 0. We can now set each factor equal to 0, and we get that sine of x is equal to 0, and 1 plus 4 cosine of x is equal to 0. Okay, from there, we get that on the first one, when is sine equal to 0? That happens when x is equal to 0. And remember, we're only looking at the interval 0 to 2 pi. So sine is 0, at pi, and 2 pi. Since we're including 0 and 2 pi, technically those are also answers, solutions here. And then for cosine of x equal to negative 1/4, we don't know this from the unit circle, so we're going to have to use our inverse cosine here to figure out this answer. So solving for x, we're going to get that x is equal to arc cosine of negative 1/4, and then also x is equal to 2 pi minus arc cosine of negative 1/4. Remember, if you compute this arc cosine negative 1/4 in your calculator, you're going to get a second quadrant angle. But cosine is also negative on the third quadrant, so we can find the other solution that is also in an interval from 0 to 2 pi by subtracting the first answer from 2 pi. And we can have approximations of the angles in radians here. So there you have it. Now, having solved for the second derivative equal to 0, we plot those points now into our number line, and we're going to get a few intervals here where we need to pick one number within each interval to test on our second derivative. Okay, so I'm picking pi 6 on the first interval, and 5 pi 6 on the second interval, 7 pi 6 and 11 pi 6. So just make sure that you have, and I'm trying to pick angles or numbers that are known from the inner circles, as I'm going to have to evaluate them in my second derivative. So these all these angles test values that I picked are from the inner circles, so it'll be a pretty straightforward evaluation here. So evaluating all those in my second derivative, starting with pi 6 here, I'm going to get, and you can verify this with your calculator, or just do it separately. But the second derivative at pi 6 is less than 0. F double prime of 5 pi 6 is greater than 0, or positive. F double prime of 7 pi 6 is less than 0. And the second derivative at 11 pi 6 is greater than 0. Looks like it alternates signs here on the second derivative, which is going to indicate concavity. So we have negative, positive, negative, positive. So it's changing on every single solution here that we got from the derivative, or the second derivative being equal to 0. Now, since 0 and 2 pi were the endpoints of the interval here, we're not going to consider those. We're not considering what happens before 0 or after 2 pi. So we're not counting those. But the pi is right in the middle of that interval, and we see the change in concavity. So that's going to be a point of inflection. And so are these two here with the arc cosine. As you can see from the number line, there's a change in concavity there across the board there. So we get, and then of course you can find the actual point order pairs by putting this x values into the calculator, evaluate them into the function to find the actual order pair. So you can do that, but there they are. Those are the points of inflection. There you have it. All right, guys, so we finally get to our second derivative test, which is presented as a theorem here. Given a function such that the derivative of f at c is equal to 0, and the second derivative of f exists on an open interval containing c. If the second derivative evaluated at this c is greater than 0, then f has a relative minimum at that point c comma f of c. If the derivative is less than 0, the second derivative at c is less than 0, then f has a relative maximum at that point. If the second derivative at c is equal to 0, then the test fails, meaning it's inconclusive. We can't determine whether there's a min or max. There could be a min, there could be a max, or neither. So we're going to have to go back to our first derivative test from the previous section to determine extrema. Right, so here we have an example where we want to find all the relative extrema of the function, and we want to use the second derivative test, assuming it applies. So finding our first derivative here, our function is f of x equal to x squared times e to the negative x. First derivative, we're going to have to use product rule. So f prime of x will be equal to 2x e to the negative x plus x squared times negative e to the negative x. Again, that's just our product rule right there. We can go ahead and factor e to the negative x, since that's what's common in these two terms. And actually, we can also factor an x as well. X times e to the negative x factored out, and that times gets multiplied by 2 minus x. And we're factoring this because we want to find when this is equal to 0 first, to find those c points from the second derivative test. In other words, the critical numbers here. So by setting this first derivative equal to 0, we're finding some critical numbers, and we get that x is either equal to 0 or x is equal to 2. Notice how e to the negative x will never be 0 or negative, so we can disregard that term there. These are the only two critical numbers that give us a solution for that first derivative being equal to 0. Okay, now finding the second derivative, because we're going to have to evaluate these two numbers that we found, x equal to 0 and x equal to 2, into our second derivative. So we need to find first what the second derivative is. All right, so look at the first derivative on the left here. Finding the second derivative, we're going to have to do a couple of product rules here. So we have two terms on the first derivative, which are products of functions here of x. So taking the derivative of 2x e to the negative x, we get 2 e to the negative x plus 2x times negative e to the negative x. Then minus, and we've already done that one already, so we just write that from that first derivative that we calculated, and we start simplifying, combining some terms here. All right, so cleaning this up a little bit and expanding everything, we're gonna end up combining a couple terms there, and notice how everything has a e to the negative x in common. We factor that out and we get a nice quadratic there as a factor, x squared minus 4x plus 2, all that being multiplied by x by e to the negative x. Okay, now that we have our second derivative, we're going to evaluate those critical numbers in that second derivative. And again, guys, that should have been a double prime in there, small typo in there. So f double prime of 0 is equal to, just plug in 0 for x, and your second derivative, we get that whole thing is equal to 2, which is greater than 0. Okay, and the same way we're going to do the second derivative of 2 is equal to e to the second negative 2 times that whole quadratic when x is equal to 2. So just plugging all that in, evaluating, we're going to get that's equal to negative 2 e to the negative 2, and that's going to be negative. All right, so using our second derivative test right here, we see that the second derivative at 0 is greater than 0. In other words, it's positive. So we're going to have a relative min in there. And our second derivative at 2 is negative. So by the test, the second derivative test, we should have a relative max in there. Now, of course, formally, you can write the order pairs by just plugging those x's into your function. We're going to get that the relative min is 0, 0, the origin, and the relative max is 2, 4 e to the negative 2. And there you have it. All right, here we have another example of a nice polynomial function, f of x equal to x to the 4th minus 4x cubed plus 2. We're still trying to find the relative extrema using our second derivative test. Okay, so first we find when the first derivative is equal to 0, so we find the first derivative, and that's equal to 4x cubed minus 12x squared. Factor the 4x squared out and set that equal to 0. So I forgot to set that first derivative equal to 0, but you get the idea. If you set those two factors equal to 0, we're going to get that x is equal to 0 and x is equal to 3, right? Those will be our critical numbers here from the first derivative. Now we're going to find the second derivative, and this process is very straightforward for functions as nice as a polynomial here, functions. So finding derivatives is a very straightforward process. F double prime of x would be equal to 12x squared minus 24x. Factoring out the 12x, we get 12x times x minus 2. Now we're going to evaluate our critical numbers into our second derivative, and we'll start with 0. So f double prime of 0 would be equal to 12 times 0 minus 2. So all that is equal to 0. And in the same way for x equal to 3, we're going to evaluate 3 on our second derivative, and we get 12 times 3 minus 2, and that's equal to 36. Now, right away we can see 36 is greater than 0, so by our second derivative test, there's going to be a relative min right here at x equal to 3. But since we got that second derivative of 0 is equal to 0. By the second derivative test, I can conclude whether we have relative min or relative max in here. So the test is inconclusive at that point. And so we're going to have to go back to our first derivative test, remember from our previous section, to determine whether there is in fact an extrema right there at 0, at x equal to 0. So we're just going to look at the 0 there, right? We've already determined that at x equal to 3 there is a min. And take a point, a test value before and after 0 on the interval before 0 and the interval after 0, and evaluate those test values at your first derivative. Remember, this is what we've practiced on the previous section with the first derivative test. So doing that, we're going to get that f prime of -1 is equal to 4 times -1 squared times -1 minus 3. All that's equal to -16, which is less than 0. We'll do the same thing for 1. F prime of 1 would be equal to 4 times 1 square. It should have been 1 square there, guys, times 1 minus 3. And that gets us -8, which is also negative. Therefore, we don't have a change at 0. And just to double check here, we already determined using the second derivative test that at x equal to 3, there's a min. But I'm just testing just to double check with the first derivative test, something before and after 3. And we already checked 1 before 3. Now we check 4. That's a 64 is positive. There is a change there in sign on the first derivative. It goes from negative to positive. So then we have a relative min right there, right? So that confirms what we already knew. And for x equal to 0, there's no extrema. So it's neither. So we can formally say that the point 0, 2 is not an extremum, and the point 3, -25, which is the y value there, is a relative min. And of course, there's no max here for this particular function. There you have it.